Today's video is going to be to do with basically all of the functions that vitamin B2, also known as riboflavin, has on the body. Now, to look at riboflavin as a structure, you'll notice the name riboflavin. These represent two different parts of the molecule. The ribo part of the name represents the ribo's tail. You'll notice all of the hydroxyl groups. This looks like a polyol, looks like maybe something like xylitol, but it is part of a ribo's tail. It's just got the aldehyde sort of head chopped off. Now, the other part with the three rings, this is known as a flavin moiety. Now, to explain the flavin moiety, you're going to have an orthobenzene rings, and this is where the two methyl groups are sort of on carbons that are next to each other. And then the middle ring, it doesn't have a specific name, it's just got a nitrogen on the top and a nitrogen on the bottom. These are very useful for when it comes to the whole part of when it's actually in its active form and how it actually works as a coenzyme. And then the ring to the right, this is actually an imide ring. It contains an imide functional group where it's got two oxygen carbon double bonds and then a nitrogen connected to it. That is a pretty rare functional group that comes up in organic chemistry, especially so in biochemistry. They're very common in ringed structures. They're not really that common when it comes to just on its own. But that essentially is the structure of riboflavin. Now, riboflavin, because it's a B vitamin, it is a water-soluble chemical. It's got quite poor water solubility, but it's still a water-soluble vitamin. It can still be excreted in your urine. This means you're more likely to be deficient in it than a chemical such as vitamin A, for example, which is fat-soluble, or vitamin D, which is fat-soluble, for example. You're more likely to be deficient in it, and you're less likely to have hypervitaminosis with it, which is actually in excess of vitamins or specific type of vitamin in your body. Now, if you had a riboflavin supplement, you'd notice that when you go to the toilet, your pee actually comes out yellow because riboflavin is a yellow pigmented chemical. I think the flavin part of the chemical, the moiety, that absorbs and reflects some kind of wavelengths of light that mean that you will see it as yellow. And riboflavin as a dried solid, as a pure solid, is a yellow substance. So that's why that happens, and don't think that you're going to be ill if you're taking any riboflavin supplements and you notice that happens sort of a couple hours or something after you take that supplement. Now, some natural sources of riboflavin are yeast and eggs. These are two foods that are incredibly high in vitamin B2, and I have eggs every single morning, so I'm not worried about my vitamin B2 intake whatsoever. Now, some artificial sources of vitamin B2, obviously vitamin B2 complexes, supplements and stuff like that, but you're also going to have artificial sort of vitamin B2, synthesized vitamin B2 inside of things like white bread. Whenever white flour is used, white flour has to be fortified with certain chemicals such as niacin, iron, and vitamin B2. And vitamin B2 is the chemical we're talking about today, and that means that people who are quite addicted to like the carbs and the wheat, they eat a lot of flour, they have quite a carb-based diet, they're not going to be deficient in vitamin B2 because vitamin B2 is one of the chemicals that's not so commonly found inside of refined carbs and carbs in general. Now, to start with vitamin B2's story in the body, it is an incredibly easy chemical to absorb. It's binded to a chemical in the sort of mouth, in your saliva and stuff. I think it's like albumin or something, and then that will be cleaved from the riboflavin part. Albumin and riboflavin will be separated by HCl in the stomach, and then it will be absorbed in the duodenum relatively easily. There is almost no problem. There's a couple transporters that it needs to like go through and stuff, but that's just to get through from the gut lining to the bloodstream, and then once it's there, that's when it can sort of do a lot of its functions. Now, why is riboflavin so important? Now, as a B vitamin, it is an energy producing vitamin, and this means that somewhere along the line of your bodily processes, it is used to produce energy. But riboflavin itself is not in its active form. It has to be converted into chemicals known as FMN and FAD, which then is converted into FADH2 to actually participate in these coenzymatic chemical reactions that are used to produce energy. So the first step in this sort of process to get to its active form is riboflavin and an ATP will be turned into FMN, which stands for flavin mononucleotide plus ADP. This reaction is catalyzed by the enzyme riboflavin kinase. Now, FMN itself has a couple of specific functions that I'm going to go through now. FMN is utilized inside of the complex 1 of the electron transport chain, which is where NADH converts into NAD to then release energy. FMN is actually what collects the H part of NADH, and it will then become FMN turns into FMNH, and that releases energy. As well as this, it is also used in the conversion of pyridoxine phosphate to pyridoxal phosphate. Pyridoxal phosphate is a very useful chemical when it comes to transaminase reactions, and it is a critical chemical in the enzymes that are involved in these transaminase reactions. So without vitamin B2 and FMN, you can't really have pyridoxal phosphate working properly, as there won't be enough of it produced. Now, I can't remember the enzyme that relies on FMN to actually convert these two chemicals into each other. Now, other than those two functions, FMN is not really that useful, and the real sort of use and the chemical that is most active inside of the body will be FAD. FAD is made from FMN plus an ATP molecule turning into FAD plus an inorganic pyrophosphate molecule. This reaction will be catalyzed by the enzyme FAD synthase. Now, FAD has a lot more functions in the body than FMN does. Now, one of the probably most well-known reactions that FAD and FADH2 participate in is in the citric acid cycle with citrate dehydrogenase. This is a reaction where citrate turns into fumarate, and FAD is sort of the starter molecule that turns into FADH2 because it collects two hydrogen molecules off of citrate. Now, the way that this dehydrogenase reaction works is the flavin moiety can sort of change its shape. There'll be certain double bonds that will be removed or changed different positions. There's a good image that I'll get up for you at some point, and it will show you the sort of where the hydrogens actually come from in FAD compared to FADH2, and that shows you how it can collect the hydrogens off of these molecules. I won't go into the whole entire mechanism of how exactly it does that, because it's quite hard to find those sort of literature papers and stuff like that to see how it actually does that, because it's understandably so. You're not going to know exactly how that works because it's something that only really goes on inside of the human body, so it's going to be hard to assess that and understand that, but we just know that that's what happens, and we know that a chemical such as FAD and FADH2 and its properties, we know that that's how it's going to work. We just don't know why it is exactly that way. Now, FAD is also useful inside of pyridoxal phosphate excretion. The step from pyridoxal phosphate to become another chemical, which I've forgotten the name of unfortunately, requires FAD to turn into FADH2 to actually excrete this chemical and make it more water soluble or water soluble enough to be excreted in the kidneys. So that is why FADH2 is important, because otherwise there's going to be a build-up of pyridoxal phosphate in the body, which is clearly not something that your body wants whatsoever. As well as this, it is useful in the pyruvate dehydrogenase complex, one of the most important sort of enzymes that actually exist inside of your body. Now, I don't exactly know how it happens, what takes what from what to what or whatever, but I know this whole entire reaction uses pyruvate to go into acetyl-CoA. And if you watch the video that I've done on thymine, thymine is like the main coenzyme in this reaction and actually interacts with the pyruvate and acetyl-CoA molecules, as in chemically, like there will be covalent bonds involved. However, I'm not aware at all of how FAD and FADH2 is involved, but I know it just is. It's probably one of the most important enzymes in the world, pyruvate dehydrogenase, and so clearly there's going to be a lot of things that are needed to actually make this enzyme work. Another function that FAD and FADH2 has is that it is utilised in the first step of beta oxidation, where fatty acyl-CoA molecule, acyl can mean that it has any length of sort of carbon chain off of the carboxylic acid group. This will then convert into something that's dehydrogenated or whatever, but FAD and FADH2 is necessary for this reaction, as again it is a dehydrogenase reaction, so you know it's going to be collecting hydrogens for the sort of molecule to actually dehydrogenate, and then this beta oxidation process is going to continue until you have acetyl-CoA completely, that the entire fatty acid molecule is going to have been converted into acetyl-CoAs. So therefore you're going to need a lot of FAD to actually make sure this process is completed completely, as well as in all of the different fatty acids that exist inside of the body, inside of your diet and stuff like that. Now, another enzyme that FAD and FADH2 is involved with is retinal dehydrogenase. Now, retinal is a sort of derivative of retinol, which is actually vitamin A. So you can see how different vitamins and stuff actually end up interacting in the body. Retinal will be converted into retinoic acid. Retinal plus NAD plus H2O will be converted into retinoic acid plus NADH and an H+. Now, while I've mentioned NADH and H+, you might be thinking, well, that's not FAD, that's not FADH2, so how can that be involved in this process? What will happen is that NADH plus H+ will be added to FAD, and that will then can be converted into NAD and FADH2. I think it's just because NAD and NADH are higher energy molecules, and this must be a higher energy reaction with a higher activation energy, and so it must need NADH to actually be able to use this process effectively. There are a couple more enzymes that FAD is involved with. You've got tryptophan to niacin, somewhere in this process between kynurenine and quinolinic acid. NADPH is used, FAD is used, it's also vitamin B6 sort of dependent as well, and that means that you can get niacin from tryptophan, which means that you won't be deficient in it. You're also going to have H2O2 protection, hydrogen peroxide, and that protects your red blood cells and stuff like that, dehydrogenates it and all that. So that is basically all of the functions of vitamin B2 in its active forms, and there are a lot more functions than I initially thought. They're all the functions of FAD and stuff like that, and now take that knowledge with what you will. I recommend eating things such as eggs and leafy green vegetables, which are all high in riboflavin, and that means that you won't end up with vitamin B2 deficiency, which is not going to be very good for your body at all, because your bodily processes just won't be able to function as effectively as they possibly could. But with that, I recommend subscribing for more content like this, and have a good day.